This is section 10.3, the final section on conic sections. Here we want to talk about this last sort of shape we have, this parabola. And so we're probably pretty familiar with the parabola already. It's just the graph of a quadratic equation, right? We've probably seen that in the past. And we know a little bit about these things already, right? The parabola opens upward if we have a positive coefficient on the squared variable, and downward if we have a negative number there. But what we want to do here is view this shape in the same sort of terms that we viewed the ellipse and the hyperbola. We want to view it through this geometric kind of definition. What is it about this shape that really makes it a parabola? What makes a parabola a parabola? Well, let's see here. A sort of geometric definition of a parabola is that a parabola is the set of all points in the plane that are equidistant from a fixed line called the directrix and a fixed point called the focus. So this picture does a great job of setting up exactly what this is describing here. It's saying this red line here I'm calling the directrix. The blue curve is our actual parabola, the usual shape we're used to seeing there. And this point up here, this red dot here, this is called the focus. Now the definition of this curve in blue is that every point on that curve I look at, its distance back to the focus is equal to its perpendicular distance to this red line, the directrix. So D1 labeled here is equal to D2. So usually we call that distance from the vertex to the focus, which is equal to the distance between the vertex and the directrix. We call that distance P usually. And if we do that, what do we have here? Well, we're really saying that by definition, let me use black here instead of pink. We're really saying that by definition, D1 equals D2. Right? The distance from our point xy back to the focus, that's D1, is always equal to the distance between our point xy and the directrix. Maybe I note here that the directrix has an equation in this picture. The directrix has the equation y equals negative p, right? It's just p units down from the origin, and it's a horizontal line there. So it's the equation y equals negative p. And the focus here, if that's also p units away from the vertex, just in the opposite direction as the vertex, like this picture shows, that focus has coordinates 0, p. So if we want to describe D1 and D2, we can just actually figure out, we're at a point xy, what is its distance to the focus? 0p. Well, we've done this before. We take the root of the pairwise differences in these coordinates squared. So x minus 0 squared plus y minus p squared. That's our D1 value, right? That's the distance between the point xy and 0p, where the focus sits. We're saying that has to be equal to the distance between our point xy and this line y equals negative p. Well, so think about what's going on here. If we have this situation, y is the distance, this y coordinate here is the distance from the x-axis up to this point. And we're just adding p units to that to get down to this line. So we could say the distance there is just whatever our y value is, plus p. Great. You can think of it as minus the negative. Top point minus bottom point. And so if you square both sides of this, what do you get? Well, this root disappears. Instead of writing x minus 0 squared, let's just write what it is, x squared. And let's FOIL this out. Well, I'll do that at the next step. Right, this is really the equation we're getting. And if I square everything out, take a hard look at everything, what do I get? That's what happens when I square this binomial. On the other side, when I square this binomial, I get this expression, and notice all the cancellation. Subtract y squared from both sides, and these guys fall out. Subtract p squared, and these fall out. And finally, Add the 2py back to this side. 2py plus 2py is 4py over here. And this is what we consider our standard equation for a parabola. Really, this equation is pretty nice. While this quadratic we know does represent a parabola in general up here, this form tells us all the important information about the parabola. Specifically that p-value, which tells us the distance up to the focus, really the coordinates of the focus. So that's where our general equation comes from, written here, x squared equals 4py. Right, let's name some things, some parts of this picture again here. Same picture that we had above. The line perpendicular to the directrix, so perpendicular to this dotted red line, and through the focus, in this case, that's just the y-axis, is called the axis of symmetry for the parabola. If this thing was shifted away from the origin, that axis of symmetry wouldn't be the y-axis anymore, necessarily. The vertex of the parabola is what we usually think of. It's this little point right down here. It's halfway between the focus and the directrix. A point P of xy on the parabola is on that parabola if the distance from a point to the focus is equal to the distance between the point and the directrix. That's the big definition. But different values here kind of make different shapes of these, different p-values make different shapes for this parabola. We'll see a very small p-value actually makes it very narrow, open very narrow, very narrowly like this. A very big p-value makes it very broad, very wide opening. So we want some sort of measure of how big these, kind of how, just a characteristic measurement of how wide these parabolas are. And that should be in terms of p. We actually call this measurement the focal length of the parabola. And that is the distance between the vertex and the focus of the parabola. Right, so from here to here. Since p is really that important value, and we'll see that there can be negative p-values, that just flips this over the x-axis. But since that p-value is what really kind of defines the shape of this, we call that p-value, at least its size, its absolute value, the focal length of the parabola. You might hear a focal diameter described for this. I think that's slightly different. I think that's 4p, if I'm not mistaken. I'd have to look back at some other references to see what a focal diameter would be called. But this is just a representative value that can let you compare different parabolas and their shapes. So here are all of our equations for this y-axis symmetry parabola with vertex of the origin. The picture we sort of derived all this stuff on. It's got all the stuff we have already discussed. The equation is x squared equals 4py, vertex at the origin. Focus was at 0p, we already said that. Directrix was at y equals negative p down here, we already said that. And the axis of symmetry was x equals 0, right? That's the y-axis. And so all that's described nicely in this picture. What I mentioned earlier, but we haven't seen visually yet, is that this all assumes, up here, this all assumes that p was a positive value, so that the point 0p is above the x-axis. Well, if p was a negative value, then 0p would be below the x-axis. And 0 negative p, the current location of the directrix, well, if p was negative, then negative of that negative would be a positive y value that we get the directrix at. So this picture just flips over the x-axis. It actually reflects perfectly into this sort of thing. This is the graph when p is negative. And all of those roles of x and y are just reversed if we want to express a sideways opening parabola. Something like in this right column here. Interchange the x and y variables in our equation, we get y squared equals 4px. And here, in the rest of these formulas, we are directly just interchanging x and y variables. That's all we do for the rest of the formulas. And all that does is interchange the roles, the role of x and y in the pictures as well. Instead of opening in the positive y direction, we open in the positive x direction for a positive p-value. Or in negative x direction, horizontally in the negative direction if p is negative. So let's scroll down a little bit further. Given a parabola defined by y squared equals 8x, let's find the focus and the equation of the directrix. We're even given the picture here. This is our parabola. Let's see if we can figure out the focus and the equation of the directrix. Well, clearly this is one of these side-to-side opening. This is opening in the positive x direction. Right, opening in the positive x direction. So a picture like this. So we know that the focus should be somewhere inside, over in this positive x region, and the directrix should be somewhere, some vertical line over here, right? X equals some p value. So let's compare this to the general equation for this sideways, this rightward opening parabola, right? In this case, we said our equation is y squared equals 4px, where that p value tells us everything about the parabola. So if we're comparing these, what does p have to equal so that these equations are equivalent? This implies that the 8 here is really like the 4p here. Divide by 4. I don't know why I'm writing things backwards. P equals 2. Right? This tells us everything we need to know. We don't even have to think about the picture, except to remember that this is sideways opening, so it's going to be, the focus is going to have an x coordinate of p and a y coordinate of 0. So we're right here. But that p value tells you how far from the focus to go, how far from the center to go to get to your focus. And the sign of p tells you the correct direction to go. Positive means go in the positive direction to get here. Negative would mean go in the negative direction from the vertex to get to your focus. So that's our focus. We know the, let's label it, let's call that F. We know the directrix is the vertical line that is the same distance away from the, not the origin always, but the vertex of your parabola. So it's a vertical line through this point, 2 units to the left of the vertex. Maybe I should have done that in red to match the previous pictures. Oh well, oh well. So that dotted line that I barely put together, that is the x equals -2 vertical line. Right? That's just negative our p-value. That's the equation of our directrix. X equals -p is the directrix in this case. So there we have it. Yeah, here we go. So to determine how wide this graph is, we said we could describe that with the what we called up here the focal length, which is just absolute value of p. But also the focal diameter is an important value. And so let's see what this length, the focal diameter being described, the absolute value of 4 times p really represents. All it is, say in this picture up here, it is the line perpendicular, I would say the line parallel to the directrix through the focus with endpoints on the parabola. It is this length. This is called the lattice rectum. The length of it is called the focal diameter, and just by some simple geometry here, you could figure out that if this distance here is p, and this distance here is p, then overall this is 2p, and this is 2p. You can figure out why all this stuff's true, meaning the whole length here is another 2p added, drawing many arrows. Overall, it is a length of 4 times whatever the size of p is. P could be negative, then that wouldn't be really a length. Negative lengths aren't what we usually consider. So we do take an absolute value there. We call that the focal diameter. So with some information about this thing, we can actually graph some of these. Let's graph a parabola with vertex at the origin, given by this equation x squared equals 16y. Let's identify the vertex, focus, focal diameter. Let's also find the endpoints of that lattice rectum that has the length given by the focal diameter. And let's write the equations for the directrix and axis of symmetry. So it's saying lay out all those table values plus this focal diameter in a nice picture. By table values, I should say all these qualities listed in this table. We want all those. So starting out at the beginning, we have x squared equals 16y. Think for a second, and maybe even try this whole problem. Pause the video and try this whole problem. If you want to do that now, because I'm going to proceed. But if we look at this and compare it to the standard form, x squared equals 4py, again, we see the 16 is playing the role of the 4p. Implies p is 4. So right away we have a lot of information. This thing is of this correct form where it's centered at, I shouldn't say centered, has a vertex at the origin. So we'll go ahead and mark that point at the origin. And we know this thing is opening in the x direction. And since p is positive, it opens in the positive x direction. Oh, I'm saying that backwards. Positive y direction, right? This is a vertical opening. This is x squared equals 4py, vertical opening. Sorry about that. This is opening in the positive y direction. So from here, that tells us how to get to our, this p-value tells us how to get to our vertex, our focus from the vertex that's at the origin. The focus will be located at 0, 4. 4 units vertically upward from the vertex. Okay, p units. And we can draw the directrix as well. That'll be 4 units in the other direction. 1, 2, 3, 4 down here. The equation of that is y equals -4. Y equals our negative of our p-value. And so our parabola looks something like, let's see, maybe something like this. Again, it should be a solid smooth curve. I'm just sketching it because it's easier to do with my device here. Oops, that's actually a little narrow for this one. Right, so maybe I should explain my thinking here. When I'm trying to sketch the actual parabola, I'm actually thinking about this focal diameter in order to get the rough size of this thing right, how narrow or wide it is. Right, the focal diameter is absolute value of 4p, which in this case is 16, right? P is 4, so you get 4 times 4 is 16. That means that when I cross the focus here parallel to the directrix drawn below, I should have a segment 16 units on center, 16 units wide, measured 8 in each direction from the center, to land with endpoints on that parabola. So at this height, I need to go 8 units out here, which would be 4, 8, which I believe is here. And I would need to go 8 units in the other direction so that we get that same distance 8 away from the focus. Now if we do that, the length of this guy is 4p, is 16 units. And that really tells us how wide this thing should be. It gives us a sense of if we're drawing it roughly correct or not. There should be a smooth curve through those points. Forgive my wobbles there. Right. So these are these endpoints that we are being asked to find. Let's go ahead and label these. We said this is at, this isn't 0, 4. This isn't 4, 0. This is 0, 4 at the focus. I think I said it right, but wrote it wrong. Over here, we need to go 8 units to the right of there. So add 8 units to that 0x coordinate. And we land at this endpoint, subtract 8, and we land at this endpoint. Our vertex here is at the origin. So the vertex is identified here. These are these endpoints we were asked to find. The focal diameter we found down here. What else do we need? The focus we actually wrote down. We labeled that here. Equations for the directrix and axis of symmetry. We have the equation of our directrix here, y equals -4. The axis of symmetry is just the straight vertical line in this case that this shape looks like a mirror image across. So the axis of symmetry is easy. It's just the y-axis, which has equation x equals 0. We have our focal diameter. We got it all here. Okay, so there's our answer. Let's do another one here. Again, this is the exact same type of problem, just a slightly different equation. Maybe you pause it and try to do this one on your own. I'm going to press ahead here and go ahead and try this though. The one little complication with this equation is it's not quite in standard form, but I hope that wouldn't trip any of us up. We can just divide by 3 on both sides and put it into standard form. But compare this to the standard general form where we have that p-value unspecified. This tells us -12 is equal to 4p. So p equals -3. This is a sideways opening parabola. So vertex at the origin, we go -3 in the x direction. Oh, sorry, -3 in the x direction. Opposite of what I did there. That's -3, right? So we know this thing's opening to the left because we have a negative p-value. The focus is always sort of inside the parabola. We could go ahead and draw that directrix 3 units in the other direction away. So that's just the equation x equals +3, I should say. That's the equation of the directrix. Here we have our focus. Now, we already found that p-value, so let's find that focal diameter. The focal diameter, remember, is just absolute value of 4 times p. The absolute value of 4 times -3 equals absolute value of -12, which is 12. So we're saying that I have to go 6 units in either direction from the focus to get to my parabola if I go parallel to the directrix through the focus. I have to go 6 units up and 6 units down to get to the curve given by my parabola. So let me go right to make up this total distance of 12. I have to go 6 in either direction. 2, 4, 6, looks like it's about here. And 2, 4, looks like we're down here. Those points sit on our parabola. We know it's opening to the left. We're ready to sketch. Just the best you can. It doesn't have to be perfect. Looks good enough to me, right? Let's label those endpoints. We were asked to find those endpoints. This looks like it's at -3 up 6. This looks like it's at -3 down 6. This was our vertex at 0, 0. We've got a lot of stuff labeled here. What else is left to label? We have the focal diameter, the focus is labeled, the vertex is labeled, found those endpoints we needed. The directrix we labeled down here, axis of symmetry. Notice in this case, the axis of symmetry is horizontal. This thing looks symmetric across the x-axis. So we would say it's the equation of the x-axis, y equals 0. Easy enough. Now what I want to see next is that these things are just as easy as the ellipse and the hyperbola to handle when we shift them to have their vertex away from the origin. Remember, the way we do it is we shift that point at the origin, that vertex, and the whole picture, the directrix, the focus, all these features of our graph move with that point. So we shift that main point and then just build everything around it the way we did here around the origin. Our equations probably aren't going to be surprising to you. It's just the same as before. If we want to shift something to from the origin to position hk, so vertex now at hk, we subtract h from the x value and we subtract k from the y value. In both of our equations, that's all we've done here. So we have nice formulas for all these things, but we're going to see it works just like the other conic sections, the other shifted conic sections. Let's jump in here and see an example. Let's take this problem 4 here. Graph the parabola. Let me zoom in. Let's get more closer view of this thing. Yeah, this is better. Graph the parabola y minus 5 squared equals 8 times x plus 2. Now, this is already of this correct form. This is like what we're subtracting from the x is a negative 2. Right? Subtract a negative. It's like addition. So that's our h value. And we're subtracting 5 from the y, so that's our k value. So this is already shifted. Think about what this would be like without those shifts there. We would just have y squared equals 8x. And that tells us, right, the 8 is like our 4p, right, compared to the standard 4px. We know that 8's playing the role of our 4p here. So we get p must be 2, solving that little equation. Already we're getting all the right stuff here, right? We know that we're going to be vertex at negative 2, positive 5. Negative 2, positive, 1, 2, 3, 4, 5. That's my vertex. P is positive, right? This is a rightward opening. Since the y is squared, we have the x here. This is a horizontal opening. Parabola, positive p-value says it opens to the right. So we can kind of picture this. This is our vertex. We're measuring all these important distances from this point now. This is like our new center, right? Our new origin. What do we measure from there? This p-value, right? That tells us the distance we need to go from here in the x direction to get to our focus. So our focus is right here, 0, 5. That's our focus. This is our vertex, negative 2, 5. Go backwards that amount, negative p, so negative 2, and that'll take you to where the vertical directrix is located. This has the equation x equals negative 2. And so we can kind of see where our parabola is going to sit. Maybe if I was graphing this, I'm seeing it's going to open up this way. So I might want to be careful. Right away, I want to be careful to see that I get those intercepts correct. It's going to cross the y-axis, even the x. I want to try to get these correct. So what I can do is say that, well, here's my focus. I know I need to go the line parallel through the focus, but parallel to the directrix, should have endpoints on the vertex that are have a distance of the focal diameter between them, magnitude 4p. So I can kind of figure out where those intercepts are going to be using my focal diameter, since they happen to sit on the y-axis. So I need to go 4 units up from here, 0, 9, and 4 units down, 0, 1, to land back on my parabola. So now I can sketch it pretty well. But over here we see I'm still going to, at some point, run into the x-axis. So before I sketch too far, I probably want to see what that behavior is going to look like. I want to see, let me fix this over here. Good enough. I want to see where is this thing supposed to cross the x-axis. So let me find that x-intercept. Remember, that just means set the y value equal to 0 in our original equation. So negative 5 squared is 25. Divide by 8. Subtract off the 2. 25/8 minus 2 is where we cross the x-axis. Well, 2 is just 16/8. 25 minus 16 is 9/8. So we're crossing the x-axis at a point just more than 1. 9/8, just more than 1, somewhere about here. Good enough, right? Good enough. Maybe we mark this. I think we've got all the good features here. We've got everything labeled very nicely. We're done. Okay. Now let's do a similar exercise to something we saw with the other conic sections. Let's take something shifted but not in a standard form and put it into standard form. Which again, we've seen this in the last video and the video before. It means complete the square on this stuff. But notice there's only one squared variable for a parabola. So you're only going to have to do this on the variable that's squared, on the y variables here. I will group the y stuff together. I'll move the constant to the other side. That's how I like to deal with this. Factor out the squared coefficient. And think about what we have to do. We have to add half this linear coefficient squared. So 1/2 of 3 squared needs to be added back on here. Okay, so that's really 9/4, right? 9/4. But what do we have? I have 9/4 being multiplied by the 4 outside. That's really 4 times 9/4 is 9 that we've added to this side. I better add it to this other side as well. Forgot my x there. Better add it to the other side as well. This is just 4 times 9/4. So now my equation gives me 4 times factor the trinomial plus 16x equals 71 plus 9 is 80. And so I want to start trying to put this in the correct form. Remember, since our y variable is squared, our correct form is going to be y minus k squared equals 4px minus h. The big defining feature of this form is that the squared variable stuff is all isolated. So I need to get rid of this 4 and move all the other stuff to the other side. So if I do that, what do I get? I have, one thing at a time, let me move that 16x over as a negative 16x. I notice in here, though, on this side of my standard equation, I need x alone, no coefficients, minus a number. So let me take the coefficient on x here, the negative 16, and factor it out of the right side. So inside the parentheses, I'll have just an x. And check my work there, that's how this binomial factors. Last little step, make sure the squared stuff's all alone, so divide off the 4 here. We get y plus 3 halves squared equals negative 4 times x minus 5. That's our parabola. That's our form that fits this. From that, you can figure out the shift to 5 negative 3 over 2. That's where the vertex went. And you can figure out the p-value from here. It would be negative 1 in this case. So not too bad, right? Let me erase that thing and say that's our final answer. That's our answer. Let's determine the standard form of an equation of a parabola with the focus given and the directrix given. We saw some problems kind of like this for the other conic sections. You're given parts of the puzzle, you have to put it together. Find the rest of the pieces and put it together. So let's draw some stuff right away to get a sense of this visually. The directrix is at y equals 6. That's the y equals 6 line. And remember, for a, well, let's wait on that. We also have the focus at negative 5, 8. So negative 5. I need a new picture. I'm going way out of bounds here. So I'll say 5 is here, 10 is here. So 6 is just above this. And we know the focus is at negative 5, 8. So negative 5 I'll say is, oops. Negative 5 I'll say is about here. And 8 is 2 below the 10 mark, so maybe about there. Now what do we know? We know that the vertex is directly halfway between the segment connecting the focus and the directrix. So if this is at negative 5, 8, the directrix is at a height of 6, so this point here is at negative 5, 6. We know the vertex is halfway in between there. Well, what's halfway between a height of 6 and 8? That would be 7. Right? This is the easiest way to piece these together, just visually. And so from here we can do everything. From here we know how we're shifted and that this is going to be opening vertically upward. So we know that yeah, let's write it out. This is the form of the equation we need to match, right, for a vertically opening shifted parabola. It's going to look like this: x minus h squared equals 4p y minus k. Something like this. So we need to find the h and k. Well, we have those already. H is where we moved the x-coordinate to. We moved it negative 5 units. So h minus a negative 4p times y minus, well, the y-coordinate we moved up 7 units from the origin. So that's y minus 7 unit shift. Minus the minus over on the left side's a plus. We just need that p-value, which we have already. Remember, the p-value tells you how far to go from the vertex to get to your focus up here. We went one unit in the positive direction, from 7 to 8 in the positive direction. So we know p is a positive 1. We're done. Plug in p equals positive 1. 4 times 1 is 4. Here is our equation. Done. So wrap up here, I just want to talk about some applications of these shapes that we've been talking about. Just a little bit more here. Let's see some applications. So the parabola has some very nice applications. All the applications I think are most important here, or maybe most interesting, most illuminating about these shapes, have to do with light and how parallel rays bounce off these shapes. So, for example, a parabola has this very unique property that if you have the focus here, I'll label that with F, and the parabola is this dark black curve, think of these pink rays as being incoming light. Light's incoming parallel, and it's all going to collect and hit this parabola, think of it as being a mirror here, and bounce off and recollect at the focus. So this is a very nice fact. This is used in telescopes, all sorts of optics. Incoming parallel light rays all collect or focus at the focus, right? That's why we call it the focus, because all this incoming parallel light is coming in. It's all going to bounce off the mirror here and collect at this focus F. So if I'm an astronomer and I want to set up a telescope of some sort, If I'm going to use a parabolic mirror in that telescope, I need to say, okay, all this incoming parallel starlight is all incoming to my telescope. It's going to bounce off my parabolic mirror. I need a little sensor to go right here at the focus to collect all the information incoming, right? All that light incoming. The same thing actually can be used in reverse to make like spotlights, for example. If I put a light bulb at the focus, then it reverses all the direction of these rays of light. Now they're outgoing from the focus. They will hit the edges of this parabola and all go outward parallel to each other. Right? It's a very nice feature. It makes this spotlight effect. Headlights use this. So that's a nice fact about parabolas. Let's look at a similar fact about ellipses. These ellipses also have some nice features regarding light and rays. It turns out if I put, say, a light bulb in the center of a ring of mirrors like this, in the shape of this ellipse, if I put a light bulb in the middle, the light will leave radially outward from this point and will bounce off the edges of the ellipse, and it will all recollect at the other focus. So we can say light, or I'll say rays, emitted from focus 1 all recollect coherently at focus 2. And so techniques like this have also been used in medicine. For example, if you have like kidney stones, you might be put into a big metal tub, like a bathtub, and be positioned very carefully so that the kidney stone is located at one focus, while a machine to generate acoustic waves, sound waves in the water, is located at the other focus. Right, if you do that, not even in water, it could just be in a dry tank. If you do that, all these sound waves recollect over here right at the other focus where you've been carefully situated so that your kidney stone is right here, and those sound waves can actually break up that stone inside, right, making it easier to deal with. So this is a very useful shape. This is a very useful fact, this ellipse. Ellipses are also very important because they describe orbits of two bodies located at each of the foci. Like a mass here and a mass here, a star here and a planet here will describe, well, I should be careful. Ellipses describe the orbits of gravitational bodies. I don't want to say what exactly those foci represent. Okay, so last shape here, the hyperbola. What are some of the nice features of the hyperbola? Think of this as being one branch of our hyperbola and having a focus here and a focus here. It turns out if you emit light or any sort of rays from one focus, if this is a mirrored surface on this hyperbola, the rays are going to bounce off of this surface and bounce outward, right? That's the solid pink lines, solid pink rays. They're bouncing outward. But the way they project outward makes it look like to an observer out here that the light rays came from this focus. What this does is gives you a very powerful tool for mirrors and optics. So long as I'm in the line of sight of this focus, I can see what's happening at this focus. Right? This is used in making fisheye mirrors for cars. For example, if I want to see this object over here, F2, but I'm pointing this way, right? My line of sight is here, right? So I can't see F2. This is like my eyeball, the direction my eyeball's opening in. Well, notice, so long as there is some line of sight back to this focus, I can follow that ray of light back in black here. It'll project backwards to this focus. I will be able to see some image of this F2 focus so long as I can keep this guy in my F1 in my line of sight. And so things that appear maybe even behind me or to the backwards and kind of beside me, because of the shape here, it makes it where I can kind of see around the corner, right? It's a very useful thing in optics and mirrors. I should mention hyperbolas, ellipses, and parabolas are actually all used to describe gravitational motion. comets and planets and things like this, the paths they follow. If say I have the sun at my focus here, a comet will follow a path very similar to this parabola, in the case that it's coming in from outside the solar system. It's going to come in and it will leave the solar system if it's got a parabolic path. If it has an elliptical path, maybe a very eccentric elliptical path, we saw an example, I believe, where we're talking about a comet coming in, very closely approaching one of the foci, and then appearing to leave the solar system for a very long time, but it's actually just a very narrow ellipse that it's following, and it goes way outside the solar system before eventually looping back again. So an elliptical orbit would actually keep something in the solar system. If it was a perfect ellipse, it would stay there indefinitely. Usually these things very closely approximate the orbits. A hyperbola is similar to the idea that we had with the parabola. I can have a comet coming into my solar system and then leaving my solar system in one shot, never coming back. But this is a little different than the parabolic path because it ends up entering my solar system along a straight line and leaving along a straight line. Or approaching a straight line. The asymptotes of this hyperbola. That's not quite the case for the parabola. It's a little different shape here. Okay, so those are some of the reasons we actually like these shapes. I hope at least the optical interpretations are somewhat interesting, how rays are treated here. Interesting stuff. Maybe you get to work with this a little bit in your future, or at least in this section. All right, that's it for this video, and that is it for conic sections.